Greetings. Today I'm going to show you how to set up a Trion T20 FPGA phase lock loop. I'll be using this little board right here I designed. It has the T20 and a QFP 144 pin package. This also has 16 megabytes of HyperRAM right here with 4 LEDs. I'll use 2 of them for locked and no lock condition for the phase lock loop. Has a SPI flash right here for the bit stream that the FPGA uses to configure itself, and a FT4232 quad high-speed interface chip for interfacing to the SPI flash. Also has a JTAG interface that goes to the FPGA and 2 additional serial ports that are interfaced to the FPGA and routed to the bus system. So let's get going. Let me show you the schematic and how that's going to be used. Right here is a 50 megahertz oscillator. It says 100, but it's 50 megahertz. That interfaces up here to this pin right here. This is clock 1 on GPIO L74 phase lock loop N0. I will also use this reset input and GPIO 2, 12, and 14. 2 will be used as a clock out from the phase lock loop. I will generate a 200 megahertz signal and output it on GPIO2 and look at it with an oscilloscope. GPIO 12 will be used for a phase lock loop not locked. GPIO 14 pin will be used for a GPIO or a phase lock loop locked. These are the bus signal names. The actual pins are R105, R112, and for GPIO 2 it's R94. So let's see. Let's go to the Affinix tool. First thing is we'll create a project. Call it T20 phase lock loop. We'll select the T20 Q144 speed grade I4. Once it's done creating a project, we can go into Interface Designer, start setting things up. First thing we'll want to do is create a phase lock loop block. Previously in the schematic, I mentioned that our reference clock would be coming in on GPIO L74, and that's going to be using phase lock loop TL1, and that uses resource GPIO L74. Now we can go to automated clock calculation. Let's take a look inside here for a second. We have a VCO that divides the reference clock input, which I'll change here in a second. There's a multiplier, another post divider, and then up to 3 clock outputs. Each can be set to different frequencies and can have a different phase with respect to the input clock. I'm going to turn these off for now. Put this back in auto mode. We'll start over here and change this to 50 megahertz. Turn the reset pin on, turn the locked pin on, and we'll set this to 200 megahertz, 0 degrees phase. Let's call this clock out 200 megahertz. Copy that. And we want local feedback. So that should do it. Next, we need to give it some pins. So we need a reference clock input, a reset input, phase lock loop locked, phase lock loop not locked, and then a clock out signal. So this we'll call clock in 50 megahertz. This is going to be input. Its connection type is phase lock loop clock in. And no Schmidt trigger, no pull up. We'll leave it just like that. Next one is phase lock loop locked. That's going to be an output. Let's see. Set its drive strength to 2. I think we'll be good there. Next one, let's call that phase lock loop locked not. That's an output. Give it a drive strength of 2. It should be okay. And now that reset, that's an input. It's on a LVDS GPIO, so no Schmidt trigger is allowed. Normally I'd probably turn it on because this line is a RC constant, and be nice to have that on, but that's okay, we can live without it. So that leaves clock out. I believe, let's see, did I get it? I'm going to call that's that phase lock loop output. We want its connection type is good. Let's see, its output to be a clock out. We want to set its drive strength to 4, the greatest it is, and call that right there, just like that. Make sure you get both these names right. This is our clock out name from our phase lock, from the phase lock loop. I think that should do it. Now we need to assign some pins. So that will be done through the resource assigner. Remember I said L74, and that should show up as a phase lock loop clock in. Our clock out is going to be R94. Where'd you go? Right. Oops. R94. Phase lock loop locked will be 14. That's R112. Not locked is going to be R105. And reset is on that LVDS pair transmit +0. And I believe that should do it. All pins are defined. Let's go back here. Make sure that looks okay. Sure, it looks okay. Okay. I'm going to save this. We'll do a design check. Check design. 0 issues down here. Now can generate a constraints file. Let's see, make sure everything's okay. All right. I think we're good there. Something that's interesting about the FNX tool is once you have a top level Verilog file, you can it generates a template with all the pins and everything. It's kind of nice. So top level. I suspect other manufacturers do the same thing. I'm pretty sure Xilinx does, but so if we go in here and see, go to Infinity, phase lock loop, open it up, and there's nothing there. Why is that? Oh, it's in the wrong one. Okay, there's the template. Okay. So we can copy that. Paste that, and there's our pins. Now we need to assign a few, make a few assignments. Let's see, what to phase lock loop. And RSTN equals N. Fine. Let's go. Phase lock loop locked. This will be from this. Because it's low active, I want to complement it. And because now when it's not locked, it'll be low. My phase lock loop locked not, because it's low active, will be on. Okay, there's nothing we need to do with this clock out 200 megahertz. It's been assigned by the pin resource in the interface designer. Should be okay there. I think we're set to compile. File change, whatever. Okay, so we got those two set. Got the reset. Okay, so I'm gonna set the size this. Oh, what do we got here? Oh, I forgot a. Okay. So, looks like it's gonna route this time. It's gonna generate a bit stream for us. Doesn't take too long. Let's program this. Oop, generating a bit stream. Okay. Here's our hex. Start programming that. And while that's doing its thing, once it gets done flashing programming the flash, Hopefully the lock light will come up. Probably just about done flashing. Usually takes it 30 seconds or so. We should see it reset and green LED done will come on. There it is. Now we got our, all right, the phase lock loop locked up. What I'm going to do is, let's go to the schematic here. Oops. On the oscillator, I have a pull-up to enable the output. What I'm going to do is I'm going to short these two pins together, and then the phase lock loop will lose its reference clock, and it should come out of lock, and that red LED should come on. Let's see if that works. I don't see why it wouldn't, but you just never know. Just never know. I can turn this little guy off. We don't need that. So, hopefully, let's see what happens here. And there's the red LED. It's out of lock because I've disabled the 50 megahertz oscillator. I turn the oscillator back on. It gets its 50 megahertz reference clock and locks back up. Let's check that out again. Out of lock and in lock. Okay. Not bad. Let's look at the 200 megahertz on the scope. Okay, so let's see. Let's turn. Let's go to the scope. Let's turn this on. Don't need the whole scope. So I have to get close to that 200 meg pin. So I have to use one of these type of ground clips. Okay. That's always difficult. And there's the 200 meg. Let's do some measurements here. Check out the frequency. It looks like 200 meg. About some rise and fall time. So fall time is 1.1 nanoseconds, and rise time is 1.75 nanoseconds. Nice hefty 200 meg signal. Not bad at all. Oops. Looks pretty good. I think that'll work just fine. Yeah. Scope goes out to 500 picoseconds. All right. So that's 200 megahertz phase locked loop. Next time I'll make a video showing some progress on my HyperRAM interface. I'm going to make a little menu system and implement a command processor in Verilog, and take advantage of one of the serial ports here to and make a UART for the user through PuTTY, let's say, and initialize the HyperRAM, do some memory tests, So that'll be the next video I make. Once I get that done, I'll post it online. Thanks for watching.